All right, we are close to the end of week number 3. Couple of assignments that you need to complete this week. The first one is quiz number 2 right there. That's due tomorrow, I believe. Yeah, tomorrow, January the 22nd. Is that right? Yeah, 22nd. By 11:59 p.m. Right, so please do this. And then secondly, you have homework that's due Saturday. So I know normally homework are due Fridays, but since we had a holiday on Monday, that's why I added another extra day for you to turn in the homework. So instead of Friday, just for this week, just for this homework, the due date is on Saturday, January the 23rd. Is that right? Yes. Okay. By 5 p.m. Right. So please do these 2 assignments for this week. Again, quiz is going to be due tomorrow by 11:59, and then homework is due Saturday by 5 p.m. Any questions on these 2 2 assignments? If not, for the lab today, some of you have this session today from 3 to 6. Since we don't have since we didn't have the Tuesday section this week, therefore for this week's Thursday section, I'm going to have it as a open lab session where you're welcome to join in to ask about your final project. So if you want to start with your final project, feel free to join in the Zoom session today from 3 to 6. If you have any questions on any part of the final project, you can ask them there. Okay, in the Tuesday lab section today from 3 to 6. Okay, so no experiment. So if you are in the Thursday section of the lab, there won't be any experiment today. You're not required to be in the Zoom session today. And I'll have it as an open session for everybody to start with the final project and to ask about if you want to have some discussion on the final project. Okay, feel free to join in. Any question on that one? Okay. All right. Not then. Let's finish our chapter 2, I believe, right? On snubbers. So what we did last week, we started the discussion on turn-off snubber circuit. Now you already know that this is the type of circuit you can use to minimize loss on the switch when it's turning off only. That's why it's called turn-off snubber. We talked about how this circuit operates, right? The 3 different components of the circuit, namely snubber resistor, snubber diode, and snubber capacitance. Then we discussed how this snubber circuit operates. Right, this one right there. When the switch turns off, it's charging the capacitor through the diode, right? And then when the switch is turning back on, or before the switch is turning back on, we want to make sure that the capacitor is charging through the switch, right, before we turn off the switch again, right? And by having additional, I should say, by having an additional path for the current when the switch turns off, right, that would provide the less overlapping. That would provide minimum overlapping between voltage across the switch as well as current through the switch, right? As soon as the switch turns off, you can see that current flows through the capacitor, thereby charging it and slowing down the rate of the rise of the voltage across the capacitor, which is practically the same as the voltage across the switch. And that's one way to minimize the switching loss, is by slowing down the rise of the voltage rise across the switch. What is another way to do that? Do you remember? Besides slowing down the rate of the voltage rise across the switch, how else? What else did we do to minimize the overlapping between the voltage and current of the switch?
Increase the capacitors use?
Well, that's related to slowing down, but in terms of the approach, there are two approaches, right? Number one is to slow down the voltage across the switch. Number two is to be able
speed up current.
To speed up current. Nope. To be able to, or to enable the current through the switch to change or to transition, to start the transition at the same time as the voltage. Right? I believe I have it on the previous page, right there. Right. So the first approach is to slow down the rate of rise of the switch voltage, and secondly, to allow current, switch current in this case, to decrease as soon as voltage increases. Right. So those are the two approaches, and as you learn from this section, snubber provides both. That's what's nice about snubber. So we talked about the effect of increasing capacitance right there, and you cannot just keep increasing capacitance, because then that would limit the duty cycle as well as increase loss. And I don't think we have talked about snubber losses yet, but that's I believe what we discussed last week. And then we went through, I forgot, yeah, we went through the equations as well to be able to size the capacitance. So that's another thing that we discussed last week, was to derive the equation for the current through the switch, which gives you current through the capacitor, and also voltage across the capacitor, which is practically equal to voltage across the switch. So keep in mind that VC of t is practically equal to V switch, voltage across the switch. Reason being, the diode is almost ideal, right? Or in this case, when we did the analysis last week, we assumed that the diode is ideal. The snubber diode, right? This diode right here. Let me go back just to clarify, because we have two diodes. So the snubber diode right there is assumed to be ideal. So if this is ideal, there's no drop across it. So therefore, this node right there should be the same as that node right there, right? I should probably use my marker right there. So this node should equal to that node, right? When the diode conducts, it's a short, right? The two nodes are equal. So if that's the same, then voltage across the capacitor should equal to voltage across the switch. Okay, and that's what we are assuming last week. And again, maybe you can also add it to your notes that, you know, this is equal to, so I should probably do it, VC of t equals VQ of t, right? There you go. Equals all of these equations, right? And we define what these are, right? What these times are, TF and TX last week. I believe TF is the time when the current reaches 0, and TX is when the time when voltage across the switch, or in this case capacitor, same thing, reaches its final value. So once we derive these equations, then we could get the equation to size the capacitor right there, right? Where VF is our criterion to select capacitor, right? So typically IL is known, TF is known. The only thing that's unknown is VF. So that's something that you need to choose when you size capacitor for the snubber. Right? So what is VF again? VF is the voltage across the cap, across the snubber capacitor, when the current reaches 0. Right? So one more time, VF is equal to the capacitor voltage when the current through the switch equals 0. Right? I think I have the pictures to show you. Again, to clarify what we did last week. Yeah, right there, right? So that's VF. That point right there defines VF. Right? That's the point where we have current reaching 0, current through the switch reaching 0. Okay. So depending on how large or the level of that VF, that would determine the size of the capacitance. Any questions on what we did last week? Oh, we also did this, I believe, right? We did the equation for snub resistor. We want to make sure that when the switch is conducting, fully conducting, we fully discharge the capacitor. So that's why we are using RC time constant, because that's what you are dealing with, right? When the snubber is discharging, the circuit that you have on the snubber is an RC circuit, right? From capacitor, it discharges through snubber resistor back to the switch. So we have an RC circuit. So therefore, how long it takes for this capacitor to discharge would depend on the time constant. And I picked between 3 to 5, and I picked the constant 5. You don't have to, but in this example, I use 5 time constant. So therefore, the on time of the switch, which relates to duty cycle, if it's PWM, that's dt, T1 is equal to dt, must be larger than, in this case, or in this example, 5 times the time constant. And from there, you should be able to get the size of the resistor in terms of resistance value, right there. So now you have the 2 equations you need to design your snubber, right? Number 1 is the equation for calculating the capacitance value. Number 2 is to calculate the resistance value of the snubber resistor. Any questions on this? I believe that's it from last week, right?
I had a quick question.
Yeah.
How does resistance affect power loss? Like as you increase resistance, what happens to power loss?
Yeah, let's talk about it next, because we haven't discussed that. So after we gone through the next subsection, then let me know if you still have the same question. Is that okay?
Yeah, thank you.
You're welcome. All right, before I do that, I just remember one thing. I want to ask you for a favor. If you please, if you could please let me know if you find any typos or errors in these lecture notes in this book. Please let me know by email, or if you stop by, office hours, please let me know. I would really appreciate it. In addition to that, if you have any feedback, any suggestions, this is an always ongoing process, a never-ending process, I would say, of developing this book. And every year it gets thicker and thicker. Of course, I do have some ideas in order to improve this textbook. I just did some modifications last night for next year's version of this book. But if you do have any ideas, ideas on or suggestion on how to improve this book, please feel free to let me know. I was going to say, I forgot what I was going to say, but it will be, it'll take some time, for this book to be, more thorough, to have more thorough coverage of EE411. That's why it's important for me to get feedback from you, to get suggestion from you, right? So if you feel like, okay, for this subsection or for this section, it will be better if there's an example to clarify this concept or things like that, please feel free to do that. And I would really appreciate if you could do that this quarter. Okay. All right. So next, after we are done looking at sizing the R value as well as the C value, now comes the loss value, the loss calculation, right? Because as you know, you have, let me draw something here. Initially, you have a switch, right? You have a switch, and of course, this switch is non-ideal switch, so therefore it will give you, power loss, just PQ, right? That's power loss on the switch. And then if this switching loss is too big, right, that's why we introduce, snubber. In our case, turn-off snubber, right there, right? Right there. So after you add the snubber circuit, then you have 2 losses, right? Number 1 is the switch loss is still there, It's not going to go away. It's still going to be there. And then you have also snubber loss, like that, right? Now, why is it that why do we bother, right? Adding this snubber if it adds more loss, right? That's the question, right? And then I mentioned last week that just because we are adding a circuit doesn't mean that the total loss will be the same. Oh, sorry, will be worse, right? If you size p-snub, the snubber components, I should say, if you size the snubber components properly, then the total loss from the two, right? So let's say this is PQ prime, right? PQ prime plus P snub could be less than PQ, the original loss. Right. Again, the keywords there is that if you size, the key phrase I should say is that if you size the components of the snubber circuit properly, then it is possible for you to get this total loss to be less than the previous switching loss, right? So that's the objective, of course, right? We want to have, not only that we want to minimize switching loss, we also want to minimize the overall loss, right? So in order to understand how to get to this objective right here, we need to look at loss equations, right? So here we go. The first one is the switch losses, right? So in general, right, if you have a switch, the loss on the switch is equal to 1 over T, 0 to T, PQ of T. If this is just for turn off, then that's going to be PQ turn off, right? And then this PQ right there, that would be the instantaneous power when the switch is turning off, right? So the overlapping between voltage and current of the switch when it's turning off, right? VQ off times IQ off, right? So that's what goes here. But that's the general equation for calculating switching loss, right? Now for the case where we don't have the snubber, so without snubber, the loss on the switch, again, this is strictly for turn off. You can see that from here. Oh, before I go there, sorry, let me go back first. That equation that I just showed you right here, it just means that if you have the waveform for the instantaneous power, right, then this equation translates into finding graphically, right, finding the area under the instantaneous power function divided by T, right? So that's what this integral means, finding the area under PQ of T and then divided by T, that gives you the average power loss on that switch, right? So let's look at the case where we don't have any snubber yet. So that's going to be, so PQT is what we're looking for, right? Instantaneous power waveform is what we are looking for here, which is right here. So this is before snubber. So you can see that when we have no snubber, then the PQ of T, again, that's just the product of voltage and current, right, of the switch. So IQ times VQ, you can see is equal to this waveform right there, which shapes exactly like a triangle, right? So it's a triangle shape for the power of the switch, power loss on the switch when we don't have snubber. So therefore, finding average power will be simple here, right? So rather than doing the integral of P of Q of T, right, where you put the equation for voltage and current, rather than doing that, now we know graphically this can be achieved by just finding the area under the triangle and then divide by the switching period or multiply by switching frequency, right? Because T is the inverse of F. So in this case, it's a simple way of calculating average power. You find the area under the triangle, which you know, right? Height times the base times 1/2, right? And then divided by the period. That's what I'm going to do for finding PQ before snubber. Okay, and take a look at the base here. The base of the triangle is TF plus TX. take a look at the height of the triangle. What is that? Anybody? What is the height of that triangle? What is it?
PQ max.
Yeah, what is the equation for the peak of that waveform?
Vmax times Imax.
That's correct. Vmax right here times Imax, right? So in this case, Vs times IL, right? So that's what I'm going to do for before snubber. Let's see. So in case you're wondering how I got to that equation, it comes from that waveform right there. Okay, so that's 1/2 of the peak times the base right there, right, over the triangle, times f, which is the same as dividing it by t, right? So any question on that first equation before snubber? All right, so that's switch loss before snubber. This one right here, right? The one I drew earlier, the switch by itself, that's this loss right there. Okay, let me use a different color now. Okay, so now, what about loss after you add snubber? Well, we need to find the same, the loss on the same switch, right? After you add snubber. How do we get that? Well, same thing. You use the same equation right there, right? Except now it's going to be more complicated, right? As you can see from these waveforms, I got 2 examples of these, I believe. Right there, see? Okay, since current through the switch changes as voltage across the switch changes, now you can see that if you do V times I, right? That's the definition of power, right? V times I. That's how I get this waveform. If you do V times I, then you get 2 linear equations, right? You have a linear equation times another linear equations. So if you multiply the 2, then you get a quadratic equations, right? So therefore, it's no longer a triangular waveform. And as you can see as well, that the peak value of this PQ of T waveform depends on the intersection of the 2 waveforms right there, right? So if the voltage across the switch is slower, of course, that peak is going to be smaller as well, right? Or lower as well, like the next example. See that? The peak is lower because the voltage across the switch is slower, right? And we talked about that last week. And what I'm trying to say is that for calculating power loss on the switch after snubber, you cannot just find the area because that's going to be hard to do, right? That's going to be hard to do to find the area here. So unfortunately for this, you're going to have to stick with the equations. And we do have the equations for this, right? Those are the equations that we discussed last week, that we derived last week's classes, one of the classes. Right? One of these, this is I of Q right there, right? That's one of the equations. We only want to look at from 0 to TF because after TF is 0, right? So if you multiply V times I, is going to be 0 anyway, so that doesn't matter, right? So just this portion right here for the current through the switch, and then for the voltage across the switch, right? Remember I said earlier that VC of T is equal to the voltage across the switch. So I use the same range from 0 to TF. That's going to be this equation right there, right? So for finding power loss on the switch after snubber, you're going to have to plug in those 2 equations under the integral. And that's what I have right here, I believe. Yeah, right there, see that? IQ, and then I believe this is VC. Yeah, this is VC or VQ, the same way, same thing. And then that's your I right there. Right? IQ, VQ, right? And it's being calculated from 0 to TF, right? And then 1 over T becomes F. And then after this, I'm just going to carry out the integration. And after that, you get the final equation for power loss on the switch after snubber. Any question on this, of how I get to this equation for power loss?
I had a quick question.
Go ahead.
Does this only apply when I and V are changing linearly? That sort of end relation?
Yes, so this is This derivation only works if the two are linear. Right? If not, then you have to change the function. Right? So it depends on what function you have for VQ, what function you have for IQ during the transition. Okay? So in this example, both of them are linear equations as we derived last week. So if you have different equations, if it's I don't know, exponential or whatever function you have for voltage, go ahead and plug it into that parameter right there. And also for the equation for IQ, you just plug it into here or substitute into that term right there, get the product, and then carry out the integral. So it could be a complicated process. It could be a complex process. It just it's just that for this example, it's just for this example, since the two are linear, it's not that bad to integrate the two, the product, I should say. Let's go ahead, sorry.
So is this the power loss of the snubber, or is it PQ prime, or is that together?
PQ prime, yes.
Okay.
So this is after the snubber. This PQ right there, which I call PQ prime there, is this equation right here.
Okay.
Right? Whereas the initial PQ is right here. Whoa, right there. Yeah. Okay.
Mm-hmm.
All right. So now I'm done with PQ before, PQ after snubber. One thing that I need to find now is P snubber itself, right? So how do we find the loss on the snubber? Well, the loss on the snubber, if you think about it first before we go into the math, right? Physically, right? Let's take a look at how we analyze the circuit first without going through the equation yet. If you look at the circuit itself, right, there's the snubber circuit. Let me erase some of these. Okay. Here's our snubber circuit, right? As we are turning off the switch, we are charging this capacitor, right? And as you know, capacitor stores energy. Right? And this energy has to be released, right, at some point of time. Otherwise, this voltage right here, if you don't release the energy, it keeps increasing. If you keep charging this cap, this voltage across this cap will keep increasing until one of these blows first. Either the diode blows up first or the switch blows up first, right? So that's why it's very important for us to be able to discharge this capacitor when the switch is turning on, just like this picture shows you. Right? Now, energy, right? Talking about energy being stored here at some point of time, that energy has to be released, right? And this is where energy is being released right there, right? And as you can see, that energy, unfortunately, when it's being released, it goes through in the form of current, right? Discharging current. That current flows through the resistor right there, right? So because of that, the energy that is being stored here now is being used by that resistor. And that would be transformed into heat, right? And that is what we call loss, right? We're not really using that energy for the load, right? This is our load. We want the energy to be, if we could, right? We want to have the stored energy in the cap to be used by the load, right? Ideally. But in this case, no, because that energy now is being used by that resistor, and then in the process, it transforms into heat, right? Not being used at all by the load. So that's a loss, right? That's why it's called a loss, because the load doesn't even use that energy. Does that make sense? So because of that, we need to look at closely on this energy equation and how that relates to the resistor. So that's what I'm going to do, right? Because that power loss on that resistor comes from the energy that is being stored in the capacitor. Therefore, the starting point would be finding the equation for energy stored in the capacitor, which I believe everybody in this class knows, right? From physics, energy stored by a capacitor is 1/2 CV squared. Notice that for this particular circuit, the V, 1/2 CV squared, the voltage across this cap eventually will reach the supply voltage. Right? So regardless what VF is, remember what VF was? VF was what? That's our criterion, right? To size the capacitance. So that VF could be any voltage. It could be Vs, it could be less than Vs. Now, this equation for energy, since capacitor voltage will eventually reach Vs, the supply voltage, therefore, it is independent of what you choose for VF, right? So it doesn't matter what VF is, this voltage across the cap eventually will be reaching supply voltage. What I'm saying is that the energy stored in that snubber capacitance will always have voltage in the equation that is equal to Vs, supply voltage. Is that clear? Okay, so 1/2 CV squared, that V has to be Vs, the supply voltage, regardless of VF. Okay, so that's how much energy we are storing in that capacitor. And as I said earlier, this energy will have to be released, right? Delivered back to hopefully the source, right? Or through the load. But unfortunately, in this case, it does not do that. Rather, it goes through the resistor, and in the process will be transformed into heat, right? And how do you then convert from energy to power? Right. So that same energy, right, W capacitor, flows into the into the resistor, and then it's transformed into heat, right? So then how do you relate PR? There you go. How do you relate WC to PR? Well, the resistor receives the same amount of energy, but then we are interested in calculating power, not energy, right? So power is in watts, energy is in joules. And so how do we do that? Well, we know that W is related to P, right? How? Anybody knows?
W times F equals P?
W time, you said W times F?
Yeah.
Or how about W is equal to P times what?
You have to have time, right?
Yeah, delta T. I mean, Nick, you were right, but what we learn in the physics is that energy is power with respect to the time, right? So we have P delta T. So therefore, P must be equal to W over delta T. You agree? If that's the case, then what is our delta T? Here. Well, this loss occurs once every what? This process repeats once every cycle, and cycle is period, right? Switching period right there. Right. So therefore, P is equal to W over T, and as Nick says earlier, that's equal to W times F, right? Because T is equal to 1 over F. Okay, so that's how I derived power loss on that resistor right there. Right, so that's the W from the energy stored in the capacitor that is now being used by the resistor, but then that would transform into heat. So therefore, per unit time, that energy becomes power loss, right? And 1 over T is equal to F, and so therefore, the final equation for snubber loss is 1/2 CV squared times F. So this is the same as P snubber, right? If you look at the circuit for the snubber, it looks like this, right? That's the circuit, that's the snubber circuit. So out of these 3 components, right, assuming everything's ideal, then the only one that would consume loss, not consume loss, the only one that would consume power is the resistor. Right. So that's why PR represents the entire loss of the snubber. Does that make sense, hopefully? Right. Okay, now I'm done, right? I'm done finding those 3 equations. Remember, the objective is to find the 3 equations. PQ before snubber, right there. And then that equation right there, that's before. and then PQ after snubber, and then finally P snubber itself. Oh, not that one. This one, P snubber itself. Right? Any questions on that? Now we have not answered, in terms of what will be a good or proper way of sizing this snubber, right? That's going to be next. But before I do that, any questions? Okay, if not, then this is a very important equation, okay, right here. That when you select the resistor, not only that you need to select the R value, right? Just like any other resistors too, right? Especially in power electronics. You also need to size the resistor based on the power rating of that resistor, right? So you want to make sure that R is properly sized and power rating of the resistor is properly sized as well. Now, what is the significance of the R value there in terms of sizing the resistance? What effect is directly related to R value of the snub resistor? Anybody?
You know how quickly that cap gets recharged, right?
That's correct. Very good. Or discharge, right?
Discharge, sorry, yeah.
Right. So R value in ohms is important because that would directly affect how fast the snubber capacitor discharges through the switch when the switch is turning off, right? So that's why it's important. You cannot just select R randomly, right? You have to be cautious of the discharging time versus the duty cycle of the switch, right? That's the R value. The power rating of the resistor, that is important because definitely you don't want to burn that resistor, right? Keep in mind that this is related to 1/2 CV squared. What's interesting is that if you look at this equation right there, right? You see something, do you see anything interesting about that equation?
There's no R.
Exactly,
It's
there's no
unaffected.
R. Exactly, you got it. Very good, you got it. What's interesting is that in previous classes, electronics, circuits, when you calculate power absorbed by resistor, there's always the R value in it, right? B squared over R, I squared over R. But here, the determining factor is not the R value, but rather is the C value, right? Assuming, of course, F is fixed, Vs is fixed, right? In this case, the one that we are going to be designing is the C value, right? So you can see that the power rating of the resistor is no longer a function of R. It is actually determined directly from the size of the capacitance, right? Now you see the trade-off of these snubber circuits, right? We talk about the trade-off, right? If I go back to it, keep in mind, okay, PR is equal to 1/2 CB squared times F. If you increase the size of C, what's going to happen with the power rating? Obviously, it's going to keep increasing as well, right? So the resistor that you'll be using is going to get bigger and more costly. Agree? So that's kind of the downside, right, of increasing capacitor value. But watch, right? Remember this from last week? What's the advantage of increasing capacitance? You remember?
You decrease PQ, right?
You decrease PQ max, exactly. See that? These pictures right here, as you increase capacitance, right, from here to here, you can see that the peak value decreases, meaning you minimize the switch loss, right? Be careful, I just said switch loss, not snubber loss, right? So by increasing capacitance, snubber capacitance value, you decrease switch loss, PQ, right? But at the cost of, what was it again? Increasing snubber loss. So let me go back to this picture I have earlier. Because now we have the equations to analyze these circuits. You see this picture that I drew earlier, right? You have PQ and you have P snubber, right? By increasing capacitance, snubber capacitance, you decrease PQ, but at the cost of increasing P snubber, right? That's what I meant earlier by saying, when you are using snubber, make sure that you size snubber components properly, right? Because you have this trade-off between the two. As this one goes down, the other one goes up, right? And so how can we achieve this then? Right? If one goes down, the other one goes up, that's the trade-off, right? How do you achieve this goal that the total loss of the switch and the snubber will be less than what you originally had right there? That's the next subsection right here. Right, so that's the next question. How do you do that? But before I go there, just to clarify again that that's how you would size snubber resistor. So make sure you follow this equation, otherwise you're going to burn that resistor if you're not careful. If you just pick any resistor with any random power rating, then you can melt this resistor. So the next question is, how do you size this snubber properly so that you can minimize total power loss? Because at the end of the day, that's what you need to achieve, right? Minimize total power loss, P snubber plus P switch, right? So here's once we have the equations, that's what's nice about mathematical equations, right? You can see that the two equations right here, right? Power loss on the snubber is a function of C, right? And so is the switch loss right there, which is also a function of C, right? Oh, this is also good to see, right? From the mathematical equation, you can see that as you increase C, you lower PQ, but at the expense of increasing PR. You can also clearly see from the mathematical equations. But what I was going to say is that now that I have the two equations, PQ and P snubber, I should be able to plot them, right, as a function of C, right there. See that? So I plot them as a function of C, snubber capacity in picofarad, right there, from 0 to 300 picofarad. And then on the y-axis, that's going to be the loss in watts. And I have three different plots here. The first one is P snubber. The second one is PQ. That's the PQ right there. That's the P snubber. And the last one is the P total, right? P total means P snubber plus PQ, right? So that's the summation of the two. So if you add the two curves, then you get this total loss right there, right? Now, what do you see from this total loss? What's nice about this is that you can clearly see that at some value of one value of capacitor, specific value capacitor, you obtain what? Focus on the blue.
Amount of losses.
Minimum amount of what you said? Minimum amount of total loss, right? So this is what we are interested in, right? Minimizing total loss, right? So as you follow this curve, the blue line right there, you can see that at some value of capacitor, the value is minimum, or the value is the lowest right there, right? Right there. That's the point of interest, right? That's that's ideally what you want to achieve when sizing snubbers, right? And can you tell me the condition to get this? How do you get that point?
Derivative equal to 0.
Now look at the curves. If you look at the other two curves, that occurs when?
Oh, intersection.
Exactly.
I mean, you could just shoot for the intercept, right?
Exactly right there. When the two curves intersect, that's when you have the minimum amount of, the least amount of total loss. Okay, so that's what we see graphically from here. But then it'll be nice to know this capacitor value, right? Let's call it C optimize. That'll be nice, right? Yes, from this picture you can get it from the Excel sheet, right? You can actually get that capacitor value. But what if you want to have equation for this? That'll be even nicer, right? Rather than using data and then plot it into Excel. So that's why calculus is important for us here. And so as you learn from calculus, right, that in order to get the minimum of the function, what do? If you know this function right there, the function for the blue line for the total, what do? You take the first derivative of that function and set it to equal to what?
0.
0. Exactly, that's what I did right here. See that function, or the function of this blue line, the total loss right there, that function is equal to PQ plus PR, right? So the function for PQ is this one right here, just plug in from the previous page, and PR is from the top of this page, right? So you just add the two, and the minimum amount of power, right, as a function of C, occurs when the first derivative of the power with respect to C is equal to 0. So what I did here is just finding the first derivative of the equation for P total with respect to capacitance and set it to equal to 0. And at the end, you get this equation for optimum value, which is very nice to have. Right? Okay, so that's ideally what you want to achieve when sizing snubber. You can see that it's a function of the load current, the amount of time the switch current goes to 0, and switch supply voltage times some function right there, times some constant, I should say. So that's the optimum value. That's this value right here. Okay? So now we know. Now we know what that value is. Isn't that cool? Right? So just by using simple calculus, we get that optimum value. And this guarantees that you have the minimum total power loss after you add the snubber, right? And number two, it guarantees that the power loss of the switch is equal to the power loss of the snubber, right? How do I know that? Well, from this curve, right? I just told you about the condition for that. See that intersection right there? That means the two are equal. Any question on this?
Why does the optimum occur when the intersection?
Say it again.
Sorry, I was getting a little feedback. Why does the optimum capacitance occur at the intersection between the transistor and the snubber powers?
Why?
Like, why does it occur when they're equal?
Oh, I see. Well, I don't know. I mean, that's coming from the curve, right? But if you get the equations right here, right? Let's say you like this at this point, I don't know if they're equal, right? So I just derive it and I get this value. And once you get this value, go ahead and put it back into PR, and into PQ. Right? If you plug in the C value into PR and PQ, you're going to get the same value. You're going to get the same equation or the same result. And that's when we know that the two have to be equal at this point, at this optimum value. Does that make sense? From graphical approach, we know that from this intersection, right? So that's easy to see. But mathematically, as I said, you derive it first, right? And then without knowing that they're equal, you derive it first, and then at the end you get the C value, right? And then you plug this C value back into PR and PQ. And go ahead and you'll see that the equation will be the same for both. Does that make sense?
Yeah, thank you.
Okay, that's one thing that that's a good idea. I think I should add it here, just to prove, right? If I add another, just a small proof right here after this equation right there, to prove that at this capacitor value, PR will be equal to PQ. That'll be good to have. So I'm going to add that tonight. All right, thank you. That's a good idea. Any other questions? All right, if not, then I did a simulation for snubber before and after, you see that? And just to demonstrate how that snubber works in terms of minimizing switching loss, right? So before snubber, look at the what do you call it? The switching transitions during turn off, right? And look at what happened after snubber, when the snubber capacitance is 10 nanofarad. Right here. You see the amount of overlap right there is smaller, right? It's longer. That's another disadvantage, right? It's longer to finish the transition time, but the amount of overlap, right? If you multiply the two, the product of the waveforms will be less. It's not really clear here because there's no power, but I believe the next one should give you, yeah, there you go. That's the power right there. right? So before snubber, after snubber. And you can see that, what do you call it? Oh, this is the effect of increasing snubber capacitance, right? From big, smaller, smaller, and smaller. Oh, switching trajectory too, right there. This is also interesting. You can actually do that. One of the experiments we're going to do in the lab, maybe next week, is to but obtain switching trajectory with ORCAD PSpice. So you can actually do that. Here is before snubber. Look at how square the switching trajectory is, right? And look at what happens after. Nice, isn't it? Remember, you want to achieve switching trajectory that is close to ideal. Ideal means follows the axis, right? Like this. That's ideal. So the closer the switching trajectory it is, the closer they are to the axis, the better. Right? So this is what snubber circuit does. It reshapes switching trajectory. Right? Any questions on this? All right. If not, example. Okay. Let's see. A switching converter should be a switching converter. Switching converter, I'm going to fix that. Switching converter with a turn-off snubber has Vs supply voltage, 100 volts, load current of 5 amps. The switching frequency is 100 kilohertz with a duty cycle of 50%, and the switch current reaches 0 in 0.5 microseconds. So that's TF, right? The current reaches 0, so that's TF. Determine the turn-off losses without snubber if the switch voltage reaches Vs in 0.1 microsecond. So that's Tx. Switch voltage reaches Vs, so that's Tx. So now we have Tf, 0.5 micro, and we have Tx, 0.1 micro, right, for part A. Part B, design a snubber using the criterion that the switch voltage reaches its final value. At the same time, the switch current reaches 0. So that's your Vf. Switch voltage reaches final value. At the same time, the switch current reaches 0. So that's Vf equals to Vs, I believe, right? Because let's read it again. Switch voltage reaches its final value, which is Vs, at the same time that the switch current reaches 0. So that's Tf equals to Tx, right? And if that's the case, then Vf is equal to Vs. Right? So that's the condition for part B. Determine the switch turn-off losses and the resistor power with the snubber added. Okay, we're going to calculate that. All right, let's do part A. Determine the turn-off losses without the snubber if the switch voltage reaches 0.1 Vs in 0.1 microseconds. So I have the given values. Right? Let's see what that correct looks like. And then part A, when Tx, I call it Ts here. Oh, something I need to fix too. So that's the same as Tx. Tf is good. Now that's Tx, which I call Ts here. I'm going to fix that to Tx. That's what I've been calling it, right? Is it Tx or Ts? I don't remember now. Didn't I call it Tx? Anybody? Yes?
I think so.
You think so, right? I think that's what I called it earlier, Tx, not Ts. So yeah, go ahead and change it to Tx. That way you don't get confused. You know, I don't want to introduce a new name or label. So that would be Tx. So 0.1 micro. So therefore, this is the equation that we had earlier, right? Before snubber, power loss on the switch is the area of the triangle divided by T or multiplied by switching frequency. So that's what I have right here. Have a look at the power loss there, quite big, 15 watts. Right. Okay, so that's before snubber. Keep in mind, that's before snubber. All right, now we're gonna add a snubber. Well, when we are adding this snubber, we want to have this criterion that Tx is equal to Tf. Again, please change that to Tx. And so the equation where Vf is equal to Vs is this, right? So right there. So I change Vf to Vs. Okay. So from there, I get the capacitance value, 1.25, or in this case, 12.5 nanofarad, right? And then for the R value, I get for 5-time constant. I didn't actually provide that in the problem statement, but I'm assuming it's 5-time constant. If that's the case, then I get 80 ohms for snubber resistor. Any question on this part right there, part B? Right. All right, so then part C, remember it was 15 watts before. Now we're going to calculate losses after you add the snubber, right? So after you add the snubber, this is the equation for PQ, and that's the equation for P snubber. For PQ, now it's 2.08. Look at the difference, right? Before it was 15 watts, now is 2 watts. Right? That's what snubber can do for us, right? It's working great for minimizing switch loss. And from 15 to 2, that's a big improvement. But as you know, that's not the only loss that we have, right? We have snubber loss to add. So that's 6.25. But if you add the 2, right, that's what you care about, right? At the end of the day, you want to see the maximum, not maximum, you want to see the total loss from both the switch and the snubber. If you add the 2, you get about what, 8.2 something, right? Maybe 8.3, around 8.3 watts, right? If you add the 2, roughly, right? And this 8.3 watt is total loss, again, of Q and snubber. That's still less than 15 watts, right? So that's good still. That's still good, right? You save, you improve the efficiency by lowering the power loss from 15 watts to 8.3 watts after you add the snubber. Okay, so that's still good. Can we do better than this? Yes, remember, we have optimum size of the capacitance. Right? Look at what happens here. PQ is not the same as P snub, right? But in order for us to get the minimum possible amount of total loss, these two has to be the same, right? And that could be done when the capacitor value is equal to the optimum value. Did I do that here? I did, yes. So you can see that if I change the capacitance value, instead of using, was it 120 something, 120, no, instead of using 12.5 nano, right? Instead of using that, I'm going to use the optimal value by using the equation I have earlier, right there. That gives you 7.2 nanofarad, right? So go ahead and use that. And if you look at the, if you plug in that C value to the PQ equation, you get 3.608. And as we expected, if you also put that same C value on the snubber loss, you also get the same watts, and they're equal as expected. Now, what happens if you add the 2? Is going to be around what, 7.2 watts. That's even better than the 8.3 that we had earlier. Right? That's better than this. You compare the 2. Right? Cool, isn't it? So that's what you get from optimum value of snubber. Any question on this? Of course, the problem is always, from practical point of view, we tried our best to get this value, but in reality, that's going to be tough to do, right? Because that's not a commercially available capacitance value. Yeah, I gotta have to find one that's close to that value, which means that it's not going to be the optimum value. But at least we have a target to to achieve, we have a goal to achieve. Any questions on this? No? If not, that's just a curve for this example. As expected, we have this intersection that gives you the minimum amount of power loss. So I'm going to skip ahead. The turn on snubber, I will not go over this, and we will not be responsible to cover this for the first midterm, or for the only midterm we have in the quarter. Right? So you don't need to study this to prepare for the midterm. So I'm going to skip this. This snubber circuit is being used for turn on time, for the time when the switch is turning on. The previous one is for turning off. The reason being, the reason why I want to skip this, because this is not really a practical circuit. I mean, it's good to learn the concept, but as you can see, this circuit is using inductor, right? And usually this is something that you want to avoid using, right? This component right there. So I rarely see, this type of circuit is being used. However, the previous circuit, the RCD snubber, is widely used in many circuits, right? For not for turn off specifically, but for leakage spike. I'll tell you about it in a second here. But yeah, I'm not going to go over the turn on snubber. If you understand how turn off snubber works, it follows exactly the same analysis, the same procedure, right? The same approach, right? KCL, AVL, exactly the same. Time constant of the snubber, in this case, L over R instead of RC, right? And then the simulations of this to show how the snubber can minimize the loss, right? So again, I'm going to skip that. I'll skip that, and then I'm going to go over this subsection right here. As I said earlier, the turn-off snubber. Let me take my water first. The turn-off snubber. When we learn about the theory behind turn-off snubber, right, what we use is the switching, how it relates to turn-off switching transition, right? You already saw that turn-off snubber helps minimize the overlapping between voltage and current. So that's how we learn the theory or the concept behind even the derivation, right, of the equations for sizing the capacitor, sizing the resistor, and all of those, right? Those are based on specifically looking at the turn-off switching transition. However, in practical applications, snubber is being used mainly for reducing leakage spike, right? So leakage spike, if you remember, leakage spike comes from what component? Or leakage. Leakage spike is caused by leakage inductance. What component has leakage inductance? Anybody? Transformer, right? So transformer has leakage inductance, as you already learned from 410, magnetizing inductance, right? The problem with leakage inductance is that it is not coupled to anything. Right? You remember, if you have a transformer, how long do I have here? 7 minutes, okay. So if you have a transformer, so isolated topology basically, right? Topology that uses transformers, a transformer. Then this transformer has, as you learn, magnetizing inductance, core loss, right? And then it has the copper loss and leakage inductance, right? This is leakage inductance right here. Okay. Now, if you have a switch in series with that, with this primary winding, for example, then we're going to have a problem here, right? Because this leakage inductance is not coupled to anything. This one is coupled to the secondary winding, but this inductor is not coupled to anything, right? So imagine if this switch is turning on, or if this switch is conducting, right? You are storing energy, right, into this inductor, right? And what happens when the switch is off? When the switch is turned off, right? This winding doesn't matter for this winding because it's coupled to the next winding, right? So when the switch turns off, its energy transferred into the next winding. But the energy stored by this leakage inductance has to go someplace, right? So remember from EE411, right? Inductor current cannot be stopped, right? Same thing here, right? If you stop right? The current here, then this inductor get pissed off, and how do we know that it got pissed? Well, you can see it from this voltage right there, right? And as you are turning off that switch, right, this inductor refuses to stop, right? Its current has to flow, right? So current has to flow still. So how does it force? How does it try to make sure that this current keeps flowing? By keep increasing this voltage, right? So if this voltage is high enough, then electrons will jump through the air, right? Okay. And so if you're not careful, then this leakage inductance could be big enough that it could damage this MOSFET or this switch, right? Because this MOSFET, let's say, is only rated at, let's say, 50 volts, and because this inductor refuses to stop its current, then it will create voltage at this node that is larger than 50 volts. It could be 100 volts peak, right? That could damage this MOSFET. Remember, SOA for voltage is absolute, right? Remember
Is
that.
this the same reason you have to like put diodes across, like if you're driving like a solenoid with like a MOSFET, you have to put a protection diode across it for reverse current? Is this like the
Exactly, exactly. Okay. That's for freewheeling. We call it freewheeling diode, right? Otherwise, you're going to get voltage building up across that inductor until something blows, So yeah, you have to have that diode protection for freewheeling, right? So here represents a problem with isolated topology, where you have a transformer with leakage inductance and a switch in series. Can you tell me what topology has this kind of a configuration where the switch is in series with the primary winding from EE411? Let me erase that part.
Is that a boost?
No, it has to be isolated with transformer. What topology has this type of connection? You forgot? Start with F.
Flyback.
Flyback, yes. And then there's another one. Start with P.
Push-pull?
Push-pull?
Push-pull, yeah. So push-pull and flyback, they are prone to leakage spike. So be careful, right? So if you're using push-pull or especially flyback, the leakage spike could be really bad. Watch. This is an actual measurements I did in the lab. That's a flyback. And I had a flyback circuit that I have in the lab, and I measure the voltage across that MOSFET, that switch in the flyback, right? And look at what happens there. This is upside down, by the way, sorry. So this is upside down. That's voltage across the drain to source, basically this voltage right there, right? Take a look at the spike. That's how you know that leakage inductance pissed, right? So that's how you know. Look at how much that voltage compared to the expected voltage on that MOSFET. Big, right? That's like 3 times almost as much as the actual voltage. That's the actual voltage. Right? The spike happens momentarily, but it could be damaging to the MOSFET, right? If it's very high enough to damage the MOSFET, right? So how do you minimize this? Guess what? Turn off snubber, RCD. So as soon as I connect RCD, right? This is without RCD. Look at the spike. Getting less and less. You see that? Nice, right? So that's what a snubber is typically used in real world, is for minimizing, suppressing leakage spike, right? What is the trade-off of doing this? Anybody? Must be the loss, right? So now you have to think about how much loss you introduce by adding this snubber. Hopefully that loss is not too much. Otherwise, you probably want to get either get a new MOSFET, or that bigger voltage rating of the MOSFET, or maybe you pick something like this, right, where the spike is not tall enough, but is enough for the MOSFET to handle. Okay, so it's a trade-off. It's always a trade-off. Okay. Any question on this? So now you know why you see a lot of snubbers, RCD snubbers being used for isolated converter. Before we adjourn, there is also RC snubber. So instead of this snubber, instead of RCD, you also will see RC snubbers right there versus RCD. So you could do this. Absolutely, you could do that. What's the trade-off of using RC with RC compared to RCD? What is the disadvantage of using RC with compared to RCD? Anybody before we adjourn?
Is that more power?
More power loss. How come?
Because now the resistor is dissipating both ways.
Exactly. Very good, Crystal. So for RCD, when it's charging, it charges through diode. So that's practically no loss. The only loss is when you're discharging the cap. When you have RC, then you're dissipating power both in charging path and discharging path. So guess what the loss is? If the loss in this snubber is 1/2 CV square F, sorry guys, 1/2 CV square F, what is the loss here on RC snubber? Must be twice, right? So 2 times 1/2 CV square F, so that's going to be CV square F. That's the loss for this snubber. That's another section that I need to add for this book. All right, that is it for today. Any questions?